Okay, good afternoon, everyone. We're going to start on time, so respect to all of you here. So thank you very much for being here today to hear a bit about what we bring today. One of the things I really need from you guys is to be a bit open-minded with a lot of things you learned in terms of software development and practices. Because part of what we're going to discuss is like developing high-performance systems using JVM. And of course, part of it is how we integrate all those high-performance systems using a Spring framework to the rest of our company, right? And I'm going to explain that in more detail, but you need to be open-minded because many of the practices you're used to, they're not true when you're developing a high-performance system. If you really want to squeeze the performance of the JVM, a lot of things need to be made differently, and I'm going to go through over that, conceptually speaking a little bit. And that's where you can achieve like microseconds performance predictable in the P99 for executions on the JVM, including network round trips. And that's what we're going to discuss a bit, and then we're going to discuss how much this put pressure on the rest of the systems around the organization, because if you're doing a lot of requests per second in that hot path in the core of your systems, everyone around it needs to be able to digest that data in a fast way as well. Although they're not using the same techniques, you need to apply some of the techniques, otherwise you cannot keep up. So this is about it. We are Bitvavo. We are the biggest crypto exchange in Euro trade assets currently in the world, and of course in Europe, based on the Netherlands. And a little bit of the agenda, talk a little bit about us, Bitvavo, and then we're going to talk a little bit about this stack and the high-level architecture we use. And then we're going to go into this section, which is where it might have a lot of concepts that we are not used to. I hope you learned something from this, and also share your knowledge if you have experience doing those things, because it's always good to learn and share. And then we're going to start talking a bit about Spring Boot applications that we build around those high-performance systems, and how we have to optimize to extreme on those systems as well, otherwise we cannot keep up. Remember that the crypto exchange is a 24/7 business. It's not like we can have some gap to catch up if we're not processing at some moment, right? If we're processing thousands and thousands of transactions per second, if we stay a few hours behind in this in the rest of it's not legacy, but in the rest of the company where it's not what we call the hot path, then catch up is very hard because you have to process all that to catch up to be on time again. And being on time in real time, it's one of the most important aspects of a crypto exchange. Right? I'm Marcos Maia from Brazil. I'm in the Netherlands for 10 years. I'm already a Dutch European citizen with my family, like 3 kids and a dog, a full package, really big, helping the Netherlands to keep growing. I have a lot of experience in the fintech, investments and trading, banks, telecom, and startups, scale-ups. That's my passion. I like fast-paced environments where you can really do a lot, develop a lot, deliver a lot, and have that fulfillment that I had building Revel kits for airplanes when I was a kid, right? You build stuff and you see it to the end. I really like that when building software, so it's part of my passion.
Cool. I'm Lars Werkman. I'm a staff engineer also at Bitvavo. Born and raised in the Netherlands. Yeah, I love working with distributed systems. Mainly have been working with startups and scale-ups in that sense. That's quickly about me.
Okay. I don't have a clock around in front of me. I hope we can make this on time. So let's go. A little bit about Bitvavo. Yeah, you can punch me if I'm taking too long. A little bit about Bitvavo. We're a trading platform. Our main goal is to enable customers, like any retail customers, although also advanced business-to-business customers like market makers, to trade crypto assets. So you have Aeron in your bank account. You don't want to use the intermediary guy to hold your crypto. You know how much scam there's around. You want to hold the crypto yourself, right? You can go to Bitvavo, just deposit euros, buy crypto, that's done. It goes to your account, you can download to your crypto wallet, or you can leave. We also have a custodian set up. We are regulated by DBNL, if it's the same banking authority in the Netherlands. And we also are also going through the regulatory requirements of European Union around MiCA. There is a regulatory requirement kicking in for crypto assets. So we are fully compliant. We guarantee one-to-one assets deposits and things like that. So if you have one asset, we guarantee that we have one asset to back up what you have. We do all the guarantees around that. And our main goal is to really make it very simple for you to trade. It's as simple as it's a simple application. This is Bitvavo. You can see the crypto assets you can buy and sell. And you also have advanced trade. If you're a more advanced trader, you can do like limit orders and other things as well. The platform also offers that on the app. Or even APIs if you want to program bots and do direct access to automate the whole trading, right? We are the absolute market leaders in the Benelux. And we are already present in many other countries in Europe. Currently, we have close to 2 million customers. We are a 24/7 business. We trade, actually it's 275 assets now. It's more than these already. This is a bit for like a couple of months ago when I did another talk. We process in a normal time, like now, we are probably processing about $5,000 per second, with peaks of 20, 30,000 per second when things got really hot. The market is really volatile. It's especially like Elon Musk does some tweet about dogs, then it goes crazy, right? You've seen this. And then you have to be really prepared for that. So our platform needs to be very flexible in terms of being very fast to scale and downscale when it's needed. And how we do that, we're going to explain a little bit on the how we do that. We have an average about 20K WebSocket connections at any moment in time. First financial app in Benelux, and we are leaders in, I mentioned this already. So a little bit of our high-level architecture. The whole company is as simple as that. I like simple diagrams. They say a lot, right? Make it very simple. We have a Kafka broker. I think most of you at this time are familiar with Kafka. We integrate our domains through Kafka, and some domains that expose REST or gRPC if it's a more performant requirement for that integration. And that's most of our company. All the domains, when you talk about domains like payments, even parts of the exchange and the compliance or the user domain, they use very standard technology. They use Spring Boot or they use TypeScript with Nest.js. Very standard, you're all used to that. But we are going to cover a little bit what we do in certain parts of the exchange with very low latency requirements. And that's where we're going to cover a little bit, and how we integrate this very high performance part of the exchange to the rest of the company to keep up. This is a bit of our stack. We are fully in AWS, and we use like different technologies. We try to keep technology a bit boring in terms of we use technologies with no one knows as much as we can, because again, with all these requirements we have for performance, for being up to date and etc., we try to keep things as simple as possible. We like simple programming, we like everything very standard, and we try to use technologies that are proof already, and that's what we do. And we try to avoid people in general like hype-driven development, just pick new technologies that don't, then it's very hard to maintain. We have this very fast-paced environment that we need to keep, right? Let's talk a little bit, and that's where I need a bit of open-minded for you, because there's a lot of different concepts. Open to questions in the end, of course. We hope to have some time for questions. We know this brings a lot of questions, but few practices we do when we're talking about low latency. And here we're talking about processing a request when it arrives on your network buffer, processing and returning in like 5 microseconds. We're talking about really high performance. And then you need to do some crazy stuff like this. So basically, you have to remove the database. It's a no-brainer, right? Databases are fast, yes, but they're very slow for what we need to do. We need to process 200 transactions per second in a single server, in a single binded CPU thread to be able to keep up and to be fair to our customers. Because we're talking about trading, so you have a fairness. So we have to do a sequence all the executions to a single entry point to be able to guarantee ordering, to guarantee idempotence. So these are some of the techniques. We do fully in memory. This means, of course, that you can use techniques like memory map files on Linux. So it's fully Linux-based, this solution, because you have to use some low-level optimizations. This is the dev shared memory area of Linux, where you can basically share files through memory across applications. I'm going to explain a bit how we connect two applications if they are in the same like EC2 server, or how you connect to the network as well, very soon. You can do eventual syncs to disk, but in general, we do everything in memory. For inter-machine communication, we use IPC. So if I have two applications running on the same EC2, that's what we do in the hot path, because we want to minimize latencies. They do through IPC, doing a shared memory file outside of the JVM. It's using operational system. So it's not allocating memory in the JVM, creating a pointer in the application IO space, nothing like that. That's too slow, right? And that's the kind of things you have to, one of the things you have to do. Network communication is always UDP. Always you use dual card machines, because what you want to do is you want one machine to be using DPDK, which is you see here. And DPDK bypasses the kernel directly for these low levels and sends the data directly to the buffers on the network and flushes it out. So when you do that thousands of times per second, you get a lot of extra performance doing those things. So you also have to do like tuning of the MTU package size default in the network. Default is like 1,500 bytes. In general, you want the MTU size, the size of the package you're sending over the network to be at least that one full message cannot be more than one package. Because as soon as you have to rebuild this in the other side, you're also spending time. So all these low-level optimizations are really important. And of course, you do fine-tune OS and network buffers. So usually, when you talk about dual card machines, we have one card taking care of the network passing and the control of the application, and the application is actually using a separate network card path. So there is no waiting time between those buffers in the JVM, in the operational system, sorry. Other thing that it's a bit controversial, because we use Kubernetes everywhere in our company. All that other, like a lot of us use these days, right? AWS, AKS, this is really good, but yeah, if you really want low latency, it's a no-go. The performance is really hurt when you do that. So what we do is, we did tests with EC2 instances and bare metal instance, and also our partner provider of the low latency framework also did those tests. And surprisingly, it's very close. This is really like very little microseconds in difference between the bare metal and AWS, which is hard to get and expensive, and the big EC2 instance, the big ones. You get almost the same performance on the microsecond level. So we opt to do in the EC2 instance, big machines. But yeah, no containers, no Kubernetes, nothing like that in the hot path. Again, it's a little piece I'm going to show you. We do everything as a distributed state machine, which means that we run everything, and everything that happens, we have a sequence of events. It's a little bit about how Kafka works. But if you think of, because Kafka is more well known, so maybe it's easier to map in your mind. So it's an append-only structure, and the processor of that structure, if you execute that 10,000 times, you have a deterministic output. 10,000 times you process in the same order, the results are exactly the same. This is really important to guarantee correctness in this kind of environments. I'm going to explain a little bit about that as well. And we always do this as a single thread, which is, again, it's a bit counterintuitive. I asked you to be open-minded. You always think about multi-threading to improve performance, but in general, it tends to be the other way around, because you want to do things like avoid context switch. You want to be deterministic. So when you have multi-thread now and you share in state, you don't know which one will pick up first. It's very hard to control. The complexity exponentially grows. It's very hard to do. It's basically impossible, I would say. So you cannot do those things. And what you do here is, when you're using the same thread all the time with an agent that's blocking that thread, you start using the low-level caches of the CPU. You all seen, if you've been gaming, you've heard about L1, L2, L3 memory level caches. And then you have the R space of the run, and then you have the application memory space. Well, when you're doing this, and you keep executing the same process, the same logic, again and again and again, bind it to a CPU, all the data you need, it goes down to L1, L2, L3, as much as you can, and then it's extremely fast. It's nanoseconds instead of milli or microseconds, when it has to go up all the way to the application R space. So these kind of optimizations are like a bit counterintuitive in general for, I would say, 99% of the applications. But if you really want to squeeze the performance to the extreme, like we have to do, you have to use this kind of technologies. And this is not developed by us, by the way. This is being discussed in trading environments for years and years, right? This is knowledge that we acquired from years and years of stock exchanges and trading environments. So some of the design principles you have to cover here. And this is also very counterintuitive. On the hot path, we have 0 GC. There is no garbage collector. What you do is, and I see a few of you like frozen your phone because it's hard to understand, but what you want to do is, you want to be extremely predict the amount of memory you need to use. Like, you know that you can execute, for example, an order flow path, that you need certain number of objects to do up to 200,000 executions per second, for example, and you pre-allocate those objects and you keep reusing them. So you allocate the VM, it takes certain amount of memory, and it's basically flat. It never has memory to collect, because you're just reusing objects, the pointer never gets deallocated, you're just reusing them. And there is no GC impact, there's no pauses, there is no CPU concurrence for GC, there is nothing like that in the hot path. It's a bit, again, counterintuitive, you have to have an open mind for this, but it works. Smart batching in the message path, so when you're sending through the network, you might think, okay, if I want to minimize latency, I want to, every request I get, I want to push it through the network. Well, this looks true, but micro-batching, and I'm talking about microsecond batching, where you accumulate a little bit of bytes and send it faster. So you have to find this very small, and we didn't do this ourselves, that's why we use a framework, and I'm going to talk about the framework very soon, because that would be crazy that we start building all these again. Since it's out there, it's actually an open source framework. Of course, log-free algorithms, you cannot have logs. It's a bit non-blocking I/O on the message path, you never block. No exceptions, you don't handle exceptions. Basically what you do is you use a lot of counters, right? So you don't do logging, you don't do strings. I will explain a bit about strings, but you don't, basically you don't handle exceptions because you minimize what each of your processors are doing, and if there are exceptions, you're basically only executing a counter to know there was an error. And remember that I said this distributed state machine. So you can have the same input now, put in another processor that will give exactly the same output, so you know what's wrong. You can, off of the hot path, you can find out what was wrong without having to throw an exception. Let me try to make this here. I see a lot of you frozen. So you have like 10 messages, right? And you have a sequence of messages. If I execute those 10 messages in any of the machines of my distributed cluster, the results will always be the same. They are deterministic. Doesn't matter. If I take those 10, they always execute in the same order, and they give the same result. Now, if I have an error, you don't treat that error immediately. You have a counter, for example. Now with that counter, you know there was an error. What do? You take the same input outside of your hot path, and you execute, and you get the same error. And outside of the hot path, then you could put a log message and see what's going on. But you don't do that in your hot path, because you need to keep processing messages from the customers coming in. So this is kind of a bit, again, counterintuitive, but it's really important. It's not good? Yeah? Okay. Thanks. We don't do unnecessary data copies, and of course no logging, no strings. Now it's a bit too high for me, but I hope it's fine. I tend to speak louder. Well, no strings is, for example, you want to pass customer data, right? And, sorry. You want to pass customer data, and usually you have these days a GUID. So you can easily transform a GUID into longs. And then on that hot path, you're just passing integers. You never pass a string. Strings are not optimized. If you have two longs, you know exactly the space you need. So 128 bytes to process them. And you know, and it's predictable. So when you're passing a message and you want to get, for example, the customer ID, you know the first X bytes, it's where it is. You don't have to parse that object and do a mapper. You just take the buffer, you take those positions, you cut them out, and you know you can rebuild that. So this is the kind of optimization, also a bit counterintuitive, but it's really necessary in these cases. A little bit of our order flow. In the order flow is where we do those techniques. Techniques of high performance is where you do. So when you look at our systems, it's only this small part here where we have to do those techniques, because it's hard to do. You have to understand, it's not easy. It's hard to do that, and it requires a lot of low-level knowledge to do it. So it's also, you have to test a lot. You have to be prepared to, for the potential mistakes. You need experienced people doing this and reviewing it, being very precise, because you're doing thousands of requests per second. If you start doing mistakes there, and it's a 24/7 business with people's money, believe me, people get really mad about this. So you really don't want to mess up with that. And that's where we do the order flow, right? So it's about sending a buy order. This is our order management service, where it, for example, reserves a balance. The sound is not good? Okay, sorry. Yeah, it's better now? Now it's better? Yeah? Okay. Oh. Whew, I'm sweating a lot. Okay. Then what you need to understand is in our order flow, we receive a request to buy Bitcoin. We want to execute that. It goes to order management service, where it sees if you have, for example, balance to do that. Because if you don't have the money to buy, then you have to cut it down. If that works, it reserves your money, so you cannot do double buying, for example, because you could buy 2 times with the same amount of money. If we don't do that, we don't want to do that. It's very simple. We have many more rules, of course, risk profiling, etc. Then it goes to the matching engine, which keeps the books on memory and does the match. Once the match is done, okay, there is the balance reservation. These are talking to each other. I didn't put all the arrows to not be too ugly, but basically this is like reserving balances. And then it does the match. Once it does the match, it transfers the balances between accounts. So you get 10 Bitcoins, the other guys get the money. It's very much like a ledger, a double ledger, that if you work in the banking sector, it's the same principle. And then in the end, you have to release the reservation, calculate the fee, and there's a lot of things you have to do. But this is it. That's the hot path. That's where we do those techniques. Everywhere else is done. When this is done, we send a message and we start generating market data. And some of the market data need to be low latency, so they connect directly here. But some market data, they can be what we call a cold path. For a hot path, we want microsecond response time. So when you send something here, the way you receive a response takes microseconds. Here, when it goes here, it can be a low milliseconds, right? So that's fine. It's the rest of the organization. And that's where we have the code sync, what I'm going to talk about a little bit. And I think I have to speed up a bit, so
we're good.
Can time. Yeah? So yeah, what we use for the hot path, just to make it very straightforward, we use a framework called Aeron. We didn't reinvent the wheel. This was created by a brilliant guy called Martin Thompson. And he's been doing this for like, I don't know, he's been building exchanges and things since the 2000s or so. The guy is really very experienced on that. And we are just leveraging his knowledge using the framework. This is an open source framework. Go to GitHub. You have access to it. It's really powerful. And what it does is it provides certain constructions for you, very similar to Kafka. If you think about this as a producer, a consumer, this is a publication, a subscription. And this is the conductor, is like the management system where they manage positions, they manage allocation of buffers and things like that. So you don't have to think much about that. But as an application, what you're writing to is we're writing to a publication, and you don't even care how this is going to be replicated. There is a media in between, and this media can be inter-process communication, could be 2 applications on the same EC2 instance or machine talking to each other. Or it could be over the network using UDP. It's abstract away. In the application, you don't have to manage, because the framework, all this part here in the middle is the framework managing it. So what you do is you send the publication, there is a sender, then you put your application to receive on the other side, you take that byte buffer, you get the data and you do something with it. And then you push back a response. So it's, instead of having a broker in between, it's a direct communication over UDP. And all the guarantees in terms of resending packages and things are taken care for you. So this simplifies a lot to apply those techniques I just mentioned before, right? But they use everything like that. But if we do this in a single machine, and we don't use the database, that would be extremely dangerous, right? Because Well, if we lose the data, it's in memory. Now I don't know if you send an order. Let's say I deduct from your balance, and now suddenly my machine goes down. I lose the memory. I lost a track of what you're doing. Remember, we don't log anything because it's slow, right? So we don't have that. So what we have to do, we use also from Aeron what they call the Aeron cluster. What the Aeron cluster does is it does a raft consensus replication of your data in memory, extremely fast, takes microseconds. So you send something, let's say this is the leader node, this is the leader. All the clients, you don't have to manually do that because the framework takes care for you. They're sending message to the leader, that's serializing that and executing. Once the leader receives, it replicates to, for example, it's the majority, so this is a 5 node, it needs to be replicated in 3 to be a quorum. It replicates to this and this node and sends a response back. So now if this machine goes down, this other machine has the memory, has the information. So you could still lose, if potentially you lose all those machines, you could still lose data, but you really minimize that, right? And eventually, this is replicated to the 5 nodes. So usually you would need to lose the 5 machines to actually lose the data. And you can do an F-sync to disk of that memory mapped file in one of these back nodes here. So you don't affect the performance doing disk serialization, you only do outside of the hot path, right? So that's more or less how it works, and it guarantees a lot of things. And on top of that, that's where we do what we call Aeron archive. That's where you do the serialization, the F-sync to disk, so the shared memory files that you're sending the data between these processes or to different processes over the network, they are serialized to disk. And through the Aeron archive is where we connect what we say have the code sync. That's our Spring Boot application that I'm going to talk a little bit now, how we optimize it to be able to keep up, right? Because in this cluster, we can process 200 requests per second clean. Like it's really like we could be sending 200,000 requests per second, and it would be processing in microseconds with P99 stable in like 200 microseconds response time. So that's how it works. So talking a little bit about the code sync. So remember that there's an Aeron archive. So there's the output from this cluster. Let's say it's a balance update that we want to put in our database because our portfolio and things needs to have that data. One example, there's more data like market data, but I'm going to use, for example, your portfolio because you want to know in the app what you bought, when you sell, and things like that. So we send through the archive, and then we have this service that sends this data to Kafka, and it also puts to MySQL to have a permanent storage eventually. But it pushes to Kafka so any other system in the company can have access to that data as well, and it can start processing the data, right? This is a bit of a drill down on that specific service. So this is what the code sync does. This is the code sync in the middle. So there's the Aeron archive. We have a client on this side. So remember, there's the media driver that's running here. Actually, it's not running in the same process, but it's running in the same machine or in the same Kubernetes cluster. In this case, we run on Kubernetes. So it runs on the Kubernetes node, the media driver from Aeron. That's actually receiving and sending out the messages between the network. And we can receive the messages, and we create like 2 agents that they are binding to specific CPUs. They're reading that archive. They have their own offsets controlling for each one of those. Each one of them have independent control because Kafka and database have different performance, so they're completely detached from each other, and they keep their own offset. They know how much they processed, so they're reading from this guy. They know the offset, they process, they batch a little bit, and they send to the database. Of course, you have to batch here, because if you start sending every request as well to the database, performance will be very slow, and suddenly you're very behind as well. The same with the Kafka side. There's not too much here, and this is a full Spring Boot. And applying just a few techniques, like this, we can basically keep up most of the time. And we use batching, of course, and we have to fine-tune sizing. It's like batching, you have to really experiment, depending on how many tables you're batching, if you have a transaction or not. The size of the batch and how many bytes you're sending makes a big difference. Remember the network MTU package side and things like that? All this makes a big difference in terms of performance if you want to do extreme optimizations. Sometimes increasing the batch size makes things slower. So you have to really do a lot of testing around that. There is like a sweet spot where you want to be in terms of performance there. We will use object pools, of course, even using Spring. So instead of keeping allocating all the time, because you minimize GC, although you have GC on the Spring Boot, it's inevitable because the Spring itself, but it's good enough. You should apply back pressure, so you should try to read as fast as possible to output, but if the input, but if the output is starting to get slow, you back pressure on the reading side, on the input, right? So you can keep up. When this starts flowing faster, you speed up here as well. For that, you use independent agents running like a process all the time and trying to get the message and pushing to, for example, to a linked queue, and the other side is trying to process that linked queue as fast as possible. Or you can use a log buffer and other techniques that are low level, but that's really part of it. You should do like smart retries, a lot of metrics, minimize logging. So again, one thing I learned with experience in the trading world is almost everything you do through logging, not almost, everything you do through logging, you can do a metric instead, which is much faster in general if you want low performance. Because if you have metrics for counters, for example, you know exactly what's going on. If your input is receiving 10 messages and your output is 9, you know you lost a message. And if you have a deterministic environment where you can reprocess the same data, you can always find what went wrong, because you can reproduce exactly the same error outside with the same code. So these kind of things are very important to apply. Fine tuning of DB, this is very, and yeah, this is no JPA. I know there's a lot of GPA talks. It's nice, but performance-wise, it's really poor. Don't use it. Template is fine, right? Just write their SQL queries, use a Spring template, and control offsets yourself for Kafka and things like that. Well, with that said, I will give a word for Lars to wrap up.
Yes. I'll talk a little bit about optimizing, or one of our use cases that's optimizing signing. So one of the things we need to do really fast is sign a JWT token. Now, I say really fast, this is not hot pad fast. We call it warm pad. Our goal was for P99 roughly below 1 millisecond. 1 millisecond, then we would be really happy if we could get this out. And that is the whole request time. So request comes in and response goes out below 1 millisecond, preferably. And then we released it. We came out to 8.8 milliseconds. Like, ooh, not really what we were expecting. So looking into that, we saw, oh, it's actually our signing algorithm that takes a lot of time. And yeah, I will show you how we were able to optimize this to a 30x performance, and on average having requests go out at 280 to 60 microseconds, and a P99 of 990 microseconds. If you want to optimize signing, you need to know a little bit about encryption. And in general, there are two different encryption types. We have symmetric and asymmetric encryption types. In general, symmetric is fast, asymmetric is slow. Security-wise, or the way that it works is you either have a single secret or you have a public and a private key pair. Key length, yeah, they're shorter or longer. It matters for the signing algorithm, but usually it's not that interesting. And some of the popular algorithms for signing with these encryption types would be HMAC or RSA signing, which you probably heard of before. And they can both use SHA-256 or SHA-512 for that. What is good to know is your use case. It's really important. Do you need to verify this signature on a client that you can trust? In our use case, we trust all the clients. It basically only happened on our servers, so we don't need a public key. So we could immediately cross off any asymmetric encryption for that and use symmetric encryption, because we could have the secret shared on our different servers. They don't leave our environment, so it's fine to share the secret around in this use case. But of course, it's always better to write some benchmarks. The benchmark that we wrote is in using JMH. It's a popular Java benchmarking tool, and it really gives you good insights and trustable insights in the performance of different algorithms for, in this example, or anything you want to measure. And what's good to note here is the throughput. So the RS here stands for the RSA signing, so this is the asymmetric key pair, and then the symmetric are the HS, this is the HMAC signing. And you can see our throughput, this is operations per millisecond. Our throughput is around 200 times better when you use a symmetric signing algorithm. This is the benchmarking code. It's very simple, very plain. One of the notes here is use the black hole. The JMH provides a black hole API. It ensures that your code won't be optimized out when you're actually running the test. It would be a shame if you're not testing any code. It could lead to false assumptions about your code. So it's always good to consume some output of your code. But that's not all. We also wanted to optimize further using Azul Prime. Azul Prime is an implementation of the OpenJDK called Sing, or they call it Sing, and it offers us low consistent response latency, higher total throughput, and faster warm-up. Some of the techniques delivering this would be the Passes garbage collection that they have, the Falcon Jet compiler, and Ready Now. These are features that they offer that we use in both our fast hot path, but also warm and cold path. It can help all your applications perform more stable and reliably. It's very simple to enable. The only thing we added was a base image for Azul Prime in our Docker file, and we configured our application with some heap. We gave it 10 gigs of heap, and that's all. You can, of course, you have way more parameters to play around with, but usually you want to figure that out after you did some debugging. You need to know your application before you actually can start optimizing your JVM options. So they recommend just starting out with just set your max heap size, that's all, and go from there. It's a bit dark. I hoped it would show up a little bit better. But when enabling Azul, we saw basically from normally our times would be around 500 milliseconds. We saw that drop microseconds immediately to 250, 260 microseconds. The fast drop that you see, that is the warm-up time. That is the JIT compiler optimizing the code path and making it way more stable. So our throughput is way more of our request times are way more stable. And you can also see that in our memory. This application was fully built in Spring. We didn't do no garbage collection because it wasn't needed for this case, but we still want a predictable and stable memory consumption. So that's definitely here something we see. Before that, we saw a rise. We thought we might actually have a memory leak somewhere. We couldn't find it, and it seemed that the other JDK implementation that we used just wasn't releasing its heap. It would claim more and more and just wasn't releasing it. Azul Prime seems to release it nicely, or at least in our metrics. And we also have very predictable CPU usage. We can really tailor our CPU needs towards the application. They seem to be very stable and predictable. What's next? Implementing Ready Now. Ready Now is a solution from Azul Prime that allows you to do the warm-up already before you actually deploy your application. You have a test environment, you run your application there with the same kind of load you would do in production, and you can already create an image for your the JIT compiler that it takes in to say, okay, this is the code path optimizations we need, and you don't have that startup penalty anymore. You immediately go to the best possible performance. And of course, fine-tuning the JVM options. That's also something we still, for each application need to work on and improve. That's it?
Yeah. That's the most important slide.
Yeah, well, we're also hiring, of course. We're always hiring. So if you're interested,